Welcome to this lesson on indices, powers, and root. These concepts are fundamental to numeracy and appear frequently in the LANTITE. You'll learn what indices mean, how to calculate with powers, and how to work with square roots. By the end of this lesson, you'll be confident handling questions involving powers and roots. By the end of this lesson, you'll understand what indices mean, that is, what it means to raise a number to a power. You'll be able to recognize and recall common square numbers and cube numbers. You'll know how to find square roots and understand them as the reverse of squaring. You'll also learn the key index laws that let you simplify expressions with powers, and you'll be able to identify exponential growth patterns. These skills are tested directly on the LANTITE. Let's start with the basics. An index, the plural is indices, tells you how many times to multiply a number by itself. In the expression a to the power of n, a is the base, and n is the index, also called the exponent or power. For example, 3 squared means 3 times 3, which equals 9. 2 to the power of 4 means 2 times 2 times 2 times 2, which equals 16. 5 cubed means 5 times 5 times 5, which is 125. There are two special cases to remember. Any number to the power of 1 is just itself, and any non-zero number to the power of 0 equals 1. A square number is what you get when you multiply a whole number by itself. A cube number is what you get when you multiply a whole number by itself 3 times. You should memorize the first 12 or so square numbers. They come up constantly on the LANTITE. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on up to 12 squared, which is 144. For cube numbers, the most important ones to know are 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. The name square number comes from the fact that n squared gives the area of a square with side length n. Similarly, n cubed gives the volume of a cube with side length n. Let's work through an example. A school library arranges books on shelves, and each shelf holds 4 cubed books. How many books is that? First, identify the base and the index. The base is 4 and the index is 3. Next, write out the repeated multiplication. 4 cubed means 4 times 4 times 4. Now calculate step by step. 4 times 4 is 16. 16 times 4 is 64. So 4 cubed equals 64, and each shelf holds 64 books. The square root of a number is the value that, when multiplied by itself, gives you that number. It's the reverse operation of squaring. The square root of 25 is 5, because 5 times 5 is 25. The square root of 81 is 9, because 9 times 9 is 81. The square root of 144 is 12, because 12 times 12 is 144. Sometimes you'll need to estimate square roots of numbers that aren't perfect squares. For example, what is the square root of 50? We know that 7 squared is 49 and 8 squared is 64. Since 50 is very close to 49, the square root of 50 is approximately 7.1. The key relationship to remember is that squaring and square rooting undo each other. Here's a LANTITE-style problem. A square playground has an area of 196 square meters. What is the length of one side? For a square, the area equals side times side, or side squared. So we need to find what number squared gives 196. That means we need the square root of 196. If you know your square numbers, you'll recognize that 14 times 14 is 196. If you didn't know that, you could estimate. We know 12 squared is 144, and 15 squared is 225, so the answer is between 12 and 15. Trying 14. 14 times 14 is 196. so the side length is 14 meters. Now let's look at the index laws. These are rules that let you simplify expressions when you're working with powers that share the same base. When multiplying powers with the same base, you add the indices. For example, 2 cubed times 2 to the 4 equals 2 to the power of 3 plus 4, which is 2 to the 7, which is 128. When dividing powers with the same base, you subtract the indices. 5 to the 6 divided by 5 squared equals 5 to the power of 6 minus 2, which is 5 to the 4, or 625. For a power of a power, you multiply the indices. 3 squared all cubed equals 3 to the power of 2 times 3, which is 3 to the 6, or 729. And the zero index rule says any non-zero number to the power of 0 equals 1. This makes sense, because a cubed divided by a cubed is 1, and using the division law, it's a to the power of 0. Let's apply the index laws to simplify 3 to the 5 times 3 squared, all divided by 3 to the 4. First, simplify the numerator. 3 to the 5 times 3 squared, the bases are the same, so add the indices. 5 plus 2 is 7, giving 3 to the 7. Next, divide. 3 to the 7 divided by 3 to the 4. Subtract the indices. 7 minus 4 is 3, giving 3 cubed. Finally, calculate 3 cubed. 3 times 3 times 3 is 27. We can verify this by working out each power separately. 3 to the 5 is 243, 3 squared is 9, and 3 to the 4 is 81. 243 times 9 is 2,187. Divided by 81 gives 27. It checks out. Exponential patterns occur when a quantity is repeatedly multiplied by the same number. This is different from linear patterns, where you add a constant each time. In an exponential pattern, you multiply by a constant. Look at the powers of 2. 2, 4, 8, 16, 32, 64. Each term is double the previous one. The values grow faster and faster. Powers of 10 are especially useful. The index tells you how many zeros follow the 1. 10 to the 3 is 1,000. 10 to the 4 is 10,000, and so on. The diagram shows how exponential growth curves upward rapidly compared to a straight line. Recognizing whether a pattern is linear or exponential is an important LANTITE skill. Let's go through the most common mistakes students make with indices. First, do not multiply the base by the index. 2 to the 5 does not mean 2 times 5. It means 2 multiplied by itself 5 times, which is 32, not 10. Second, you cannot add indices when the bases are different. 2 cubed times 3 squared does not equal 6 to the 5. The index laws only work when the bases are the same. You need to calculate each power separately. 8 times 9 is 72. Third, don't confuse squaring with square rooting. They are opposite operations. The square root of 16 is 4, not 256. Fourth, watch out for negative signs. -3 in brackets squared means -3 times -3, which is positive 9. But -3 squared without brackets means negative of 3 squared, which is -9. The brackets make a crucial difference. Here's a LANTITE-style word problem involving exponential growth. A scientist starts with 5 bacteria, and the population triples every hour. How many bacteria after 4 hours? First, identify the pattern. At the start, there are 5. After 1 hour, each bacterium has tripled, so there are 5 times 3. After 2 hours, it's 5 times 3 times 3, or 5 times 3 squared. We can see the pattern. After n hours, the number is 5 times 3 to the power of n. Substitute n equals 4. We get 5 times 3 to the 4. Calculate 3 to the 4. 3 times 3 is 9, times 3 is 27, times 3 is 81. Finally, 5 times 81 is 405. There will be 405 bacteria after 4 hours. Now it's your turn to practice. Pause the video and try these 6 problems. Problem 1. Calculate 2 to the power of 6. Problem 2. What is the square root of 169? Problem 3. Simplify 4 to the 5 times 4 cubed using index laws. Problem 4. Calculate 5 cubed minus the square root of 49. Problem 5. A population of 10 doubles every year. How many after 5 years? Problem 6. Simplify the fraction 6 to the 8 divided by 6 to the 5. Check your answers on screen when you're ready. Let's recap the key ideas from this lesson. An index tells you how many times to multiply a number by itself. You should memorize the square numbers from 1 squared to 12 squared, and the cube numbers from 1 cubed to 5 cubed. These come up repeatedly on the LANTITE. Square roots are the reverse of squaring. The square root of n asks what number times itself gives n. The index laws let you simplify expressions with the same base add indices when multiplying, subtract when dividing, and multiply indices for a power of a power. Finally, exponential patterns involve multiplying by a constant factor, which causes values to grow faster and faster. Make sure you can confidently apply all of these concepts before moving on.